meetup.com. That doesn't work worth a darn. So, without further ado, Christopher Lozinski, who is in Europe and wanted early. So this is as early as it gets. Thank you so much. A couple of ground rules before he starts, though. Mute your microphone if you're not the presenter during the presenter speaking. If you want to, the presenter will tell you at the beginning who he is. He's got to introduce himself. That's the way we work it. If he wants to take questions during his talk, he will say so. Otherwise, don't interrupt. So mute your mic, don't interrupt. Thank you for sharing. On with the show.
So first, can you hear me?
We can hear you fine.
Super. And can you see the slides?
We have your screen with its picture of you and your credentials.
Great. So Christopher Lozinski, longtime software developer. Recently, I've gone back to graduate school for electrical engineering, digital design. I've always been interested in how computers work. Fourth is very efficient. And so let's talk about that. So the talk is about the J1 family of soft-core processors. These are fourth CPUs running in Verilog on an FPGA. And so the first question is, why would you be interested in such an obscure technology? And so the reason is, so the first thing is performance. Let's look at clock cycles. In the left column, you have ARM fourth. Basically, if you build a fourth, if you do it sort of the obvious way of each fourth instruction as a separate subroutine, in order to call an add, it's 4 clock cycles. One to call, LDM, PT, 2ND. I'm not quite sure what those two commands do, and then finally return. So that's like 4 clock cycles. This is from a friend of mine who's an assembler expert, an ARM assembler expert. Web searches indicated that's about the correct number. So that's going to take you 4 clock cycles. It's going to take you 4 instructions in memory. So it uses up both time and space. If you have an ARM-C compiler, it's going to be just 2 instructions, 2 clock cycles, 2 instructions in memory. Of course, you don't get an interpreter with ARM-C, and you also get a very large compiler. If you do an FPGA on like a J1 CPU, it's a single instruction, it's a single clock cycle, you save memory. So some advantages here. This is a place where I'd be very interested in comments. Let me go through the talk, but if you have something about the slide, I'd be very interested to hear because I'm not an assembly expert. The other place where the J1's CPUs give you a competitive advantage to say ANSI fourth are elided words. So these are a single word in J1 fourth, which actually would be 2 words in ANSI fourth, maybe G fourth or something like that. And so maybe that's giving you 8 instructions in a single clock cycle, 8 assembly instructions. Okay, but so there's some advantage to having a single fourth core, not that great, but what really happens because they're so small, if you have large numbers of them, something like the green arranged GA 144, but of course with a lot more memory, then suddenly things get very interesting. So at this point, we're going to switch to the best graphics demo I could find. Let's see if I can do this. Can you see the image? Okay, I presume that everything is okay. Let me just first introduce this. In the upper left, you have a fisheye lens. So by default, lenses do a round lens with a flat surface in the back. Receiver is going to give a fisheye unless they spend a bunch of money on the lens. And here you have an FPGA that's turning that fisheye view into a very normal view. And so you can actually see it. So with an FPGA, you can imagine doing something like that. And so, of course, you have to do that in Verilog, which is extremely painful. If you could do that in fourth with a bunch of cores, it would be much easier. Hearing aids, there's a group on the slides. On the slides, there's a link. In fact, let me make sure that everybody has. On the slides, there's a link to computational audiology, and they're considering adding an FPGA. Stereo is 16 bits. The ICE40, the FPGA I'm using, is also a 16-bit processor. It has 16-bit multipliers. And, for many of us older fourthers, hearing aids would be great. We could program. I'm getting some sound occasionally, but okay. Fourier transform is a well-known algorithm that runs very happily on multiple cores, particularly if the cores are properly connected. Sound localization is another one. Maybe think bat echolocation, but the two sounds reach your ears at different times, and if you do cross correlations between the two ears, you can figure out the angle to where the sound is coming from. And then if you're doing a hearing aid, you can deduct out all the sources that you don't want to hear and just focus on the person in front of you. And then music synthesis. Most microcontrollers only have one multiplier. If you want to synthesize a whole orchestra, you need a lot of multipliers, a lot of processors. So doing it in parallel is a really good idea. And also you need typically I2S is the standard for audio input and output. And so you really need I2S in hardware. And so an FPGA will give you that also. Okay, so which fourth core are you going to use? My previous talk here was a review of fourth soft core processors. You may have seen it. I also did that in Stockholm FPGA. And there was this table, and the one that came to the top at the time was the J1. It's really the sort of lowest cost, minimal LUTs. LUTs is a measure of logic on an FPGA. It's very fast, it's very small, so it's inexpensive. And the magic is that they use a lot of memory. Memory is hardcore, so memory in your FPGA is just as efficient as memory in your computer. But they use logic takes up like 10 times as much space as an ASIC. And so what the J1 does, it uses a lot of memory and minimal logic. So very, very smart design. It's really beautiful. It's less than 200 lines of code. It's fast. It runs at 80 megahertz. It's optimized for FPGAs. It's really conceptually gorgeous. It's easy to understand. The 200 lines of Verilog is very misleading. Most software applications are, tens or hundreds of thousands of lines of code. So I thought 200 lines of Verilog, this is great. It's easy. But it turns out that unlike software, when things happen one thing at a time, and it's really easy to debug it, in Verilog, it's really difficult to debug it because everything's happening at the same time. So don't be misguided by just 200 lines of code. And it was very much smaller than the microblaze, which was another architecture. Sure, the microblaze is 32 bits and J1 is only 16, but even compensating for that, it took up much less memory, his application. And it's also a lot smaller than like the smallest well-known register machine, the CPU, which comes in at 442 LUTs. This one's 160 LUTs, maybe as small as 80 LUTs. It's hard to actually compare different CPUs. They're all a little bit different, but the numbers are interesting. Of course, it does have a lot of limitations. It has no interrupts. It has no timer. It has no fourth. They released another version called Swap Fourth, which does include a fourth. It's only 16 instructions, and it's only 8K of memory addresses. So you could get 8K instructions, 2 to the 13th. And the J1 requires dual port RAM, which is not available on the least expensive FPGAs. Okay, so what's this dual port RAM? Well, there are different types of RAM on an FPGA. Single port is what you kind of think of as memory. You can read or write once per clock cycle. Dual port, you have 2 ports on the same block of memory, so you can read, or both can read, either read or write during one clock cycle. And then you have pseudo dual port. One port can read while one port can write during one clock cycle. So the different fourth machines have different types of ports. And if we look at the J1 family, you'll see that like the bottom are 32 bits. Some in the middle do work on this pseudo dual port. Some do dual port, but there's none that really works on like the single port memory. So that's part of what I'm working on. There's some 16 operations, fourth words that the J1 supports. Just going down the last column, the next top of stack will either be a copy of the top of stack or the next, or the sum of the top and the next, or the AND, or the OR, or the XOR, or the inverse, or it's a test of whether the next in stack equals the top. Some 8 more commands on the right-hand side. What's really sweet about the J1 is why it's so efficient. So he does a lot of really smart things. On a 16, typically on a register machine, if you load an instruction, you have one command, which is load the instruction, and then the next command, which takes another clock cycle to read the next instruction, is going to be the 16 bits. And so what he does, a lot of the fourth soft cores do this, is he adds one bit, the first bit, which says, this is not an instruction, this is just a value, load it. Okay, so then you get 15 bits. 15 bits is 2 to the, is, I think, 32,000. So pretty good range. And then the next three, he does something even better, which is the first 3 bits tell you what type of instruction it's going to be for jumps. So you get a jump, a conditional jump, or a call. And then he just slaps the 13 bits of what the address is, which means that he's limited, that the CPU is limited to 8K of words. And the fourth I'm using is about 3K of words just for the raw fourth. So you don't have that much space for your application. So maybe extending this by a bit would be good. But it does lead to a very fast processor. And then the most interesting thing is the bottom line. That's where he puts the instructions. So the first 3 bits tell you that this is actually an ALU instruction, and then skip the next one. The next 4 bits tell you what the instruction is. And then he's got 8 more bits that actually control the CPU. So you could, for each instruction, you could have the control bits in hardware, in Verilog, but what he does is he just reads them in for memory. So it consumes memory, but it minimizes the amount of logic. And so that was really, really smart design choice. A lot of people quite like his design. And then you can go through different flags. Each of the flags, the second and 2 from the far right are the data stack and the return stack. And so for each of the instructions, you can see how it impacts the data stack and the return stack. And so these are the flags that he uses to control the register. And the great thing about these flags is it gives you a very clear concept of what a register machine, what a fourth machine is. So it's really beautiful because it just sort of highlights what these stack machines can do. Very, very nicely done. And we can actually take a look at a little piece of the Verilog. So the first row is literal. You can see this in this obscure Verilog coding 8B1. So that means it's 8 bits of binary. And the 1 means the first bit is a 1, and we don't care about the others. That means it's a literal. So just whatever the last 15 bits are of the literal, that's what the next top of stack is going to be. Next one is a call. You've got the first 3 bits that tell you it's a call. And then if that's the case, the next in stack stays the same, but because we're just calling. Conditional jump, because it's a conditional jump, you're going to test whether the top is true or false, and then you're going to jump. So then the top of stack is going to be what's currently next of stack 1. And then you've got different examples of the ALU. So based on the longer bit stream, after the question mark, you've got 4 bits that tell you what which ALU command is. You can duplicate the top of stack, duplicate the next of stack, add, and, or, XOR. So it's pretty easy to look at his 200 lines of code and reasonably quickly understand what the whole thing is doing. Very nice. And so about the time he was doing this, Lattice came out with the H21K memory, and there were the open source tools, and it just turned out that it had 32 times 4 kilobits, 128 kilobits of pseudo port RAM, which is exactly 2 to the 8th, 2 to the 13th memory addresses of 16-bit RAM. So it fit perfectly with his chip. So he ported his chip to that. He worked with the open source, and so then a lot of people picked up with it, played with it, had a good time with it. And so initially he did the J1 for his own applications, and so it's closed source. He doesn't provide any source to it he has some products based on it. But then for the J1, then he released the J1A. It works with pseudo dual port RAM. It adds a 4th library, and there's even a J4.V, which is a 4-core barrel processor. So what it does is every clock cycle, it works on one of the 4 different processors. And so each one is 1 quarter as fast, but you can do a lot more IO with it. So kind of interesting stuff. Not well documented at all. But they also, both the swap fourth J1 and J1A, they're two in there. They really have their limitations. It's extremely efficient. So when he actually does a read, he has a application read, he has a problem because you're supposed to be reading an instruction every time. So when an application read happens, first you have to store the application read instruction because you're going to need it. Then you have to basically stop the process, or you have to give the memory what the address is that's supposed to read. And then the next clock cycle, you've got the data, but now you don't have the instruction, but you've saved it, so you use it. And he could have done it very simply externally, but he messed with the code, and it messes up the code. And it's just so hard to read this and so hard to understand. It's not well documented. So what was beautiful is now much more widely usable, but no longer beautiful. It's very sad. And of course, it has all those other limitations. So a lot of people are using the Mecrisp-Ice. And so it's not 16 instructions, it's got 27 instructions. It's got nice comments. J1 doesn't. It's got 16 IO ports. It's got nice variable names. It's got SPI flash and constant folding, and it uses G4. It's sort of, the J1 has Swapforth has a Python cross compiler, which is not very heavily used. It's got tail call optimizations. It's got 14 supported boards, inlining, tick counters, sort of everything you could ask for. Lots of good Forth code in there, lots of good Verilog in there. It runs on a whole bunch of platforms. So, these are all 35, 50, at most $100 boards. ULX 3S is maybe a $200 board, but lots of different boards to choose from. He recommends the Icebreaker, fine. It's got, let's see, details aren't that important. How am I doing? 18. And the great thing is Mecrisp still has a very tiny compiler. They claim 11 kilobits. I get more than that. Maybe that's because he's doing some inlining. So anyhow, but still quite small. Three kilobytes of 3K words is what I get on mine. But it also has some limitations. All the software is preloaded. If you're a Verilog developer, that's what you want to do. But for the Forth software developers, you really want to have just the bare compiler loaded, and then you can load in whatever you want based on what your applications are. So it's targeted at Verilog developers. It's not targeted at Forth developers, which is this group. And it uses a lot of LUTs. On the 5,280 LUTs lookup tables that are available in the ICE 40, it uses almost half of them. And again, you only get 8K of memory addresses, which is a bit tight for an application. GPL code, maybe that's a problem, maybe not. And it doesn't support the single port RAM. And so here's why single port RAM is. This is on the up is the what the J1 currently supports. And on the bottom, you get so much more. You get a whole megabit of memory. So even at 14 bits, you've got enough space there for 4 J1s and J1As. So that's kind of the direction I'm heading. To use all that memory. So basically my master thesis, I'm building a variant of the ICE 40 that runs on a Pico-Ice. Currently I already have one that uses 993 out of 5,280. That's only 18% of LUTs compared to the 49% that's used by the regular Mecrisp. And it runs on the Pico-Ice, which is based on the ICE 40. So a very nice little board. It comes with PMODs, so you don't have to, for $5 more, it comes with PMODs. You don't have to solder anything. And it runs with an RP2040, which you can actually run Zepto Forth on also. So the RP2040, that's the chip at the core of the heart of the Raspberry Pi. It's got 2 cores, 264 kilobytes of RAM, and you can run C or MicroPython or CircuitPython or Go or Rust or JavaScript. And it's got like 3 different versions of Forth with run on there, maybe 4 now actually. And on the right, and it also has the ICE 40K, so lots of good stuff in there. I actually have one of these to give away. So the manufacturer was kind enough to donate one. So basically, if you win this, if you're in the US, he'll mail it to you directly. And if you're in Europe, then what you do is you get a $35 credit and you can order it from China. US mail has problems. You can order from China and you have to pay shipping or something like that, maybe $5 more for the emods. So is anybody's birthday today, or whose birthday is it closest to today? Can you raise your hand? And Kevin, that part, maybe you can help me with this. Anybody have a November birthday? October birthday?
Anybody have a birthday this year?
October?
I just
I just turned 79 on the 8th. So, but I must admit, it'd be great to go and have somebody who'd be interested in doing that end of cozy on the chip rather than me. But
okay, so anybody else interested in the board?
I'm interested if you're
Okay, yeah, it's best for it to go to somebody who's interested. So who just spoke up?
Brad Nelson.
Oh, super. Okay, and thank you so much for all that you do here. So I'm really glad that it goes to you. If you email me your address, then, and also I guess you're in the US, then I'll see to it that you get it.
Alrighty, will do.
Super. Okay. Moving on. So single port RAM. I actually have single port RAM working in simulation, but the real world is harder than simulation because it turns out on these ICE40 chips you can't initialize the RAM, and so you have to read it in from the SPI flash memory. So that's what I'm working on currently. And I also want to make it 14K bits because 16K words is a bit too small, and add an I2S interface, right? So most of the real world is not 16 bits, but audio is 16 bits. Stereo audio on a CD is 16 bits. And so, you know, I get a lot of the information is in the time domain rather than in the bit resolution domain, right? And so that's what I'm focused on because the ICE40 has a 16-bit wide memory path. So it sounds like a really good application area for it. And then for another $25, you can get a PMOD, which has both stereo audio input and out. And then eventually there'll be 4 cores here. So there's one friend of mine who's very interested in doing audio synthesizers on here. So that's kind of the general path I'm going. But I'm not the only one who's working on this stuff. There are a bunch of other fourth machines out there. J1SC is done in spinal HDL, really interesting. So there's the VEX RISC-V, which won first place at the RISC-V Summit Softcore Contest. It was also written in spinal HDL. And basically, Verilog is kind of a little bit crufty, ancient hardware electronics engineers software. You can do much fancier things in Scala and spinal HDL, much more flexible. And so the J1SC actually did that, and it's got all kinds of options. But of course, when you get too many options, it gets really hard to start to use it, and there's no simple place to get started on. And so I tried to get started with it. I couldn't. So then I went back to using the Mecrisp as the basis. But in the future, that's clearly in my path, because as soon as the software gets too complex, you really need more advanced tools. But I'm not yet at that stage, so I'm not using it. Okay, so back to the J1 family, now that we kind of know what they all are. So J1 was the original one, which he did. He has products for basically what it does. It reads bits from a camera and pushes them out to UDP. J1A is the one that does single port memory, so a lot of people are using it. Mecrisp is a much more useful variant with all the stuff added back in that he took out. He's got dual ports and single ports and 32 bits and 16 bits and 64 bits and all kinds of great code and all kinds of different stacks, Verilog, lots of great stuff. On the bottom row, we've got J1B, which is a 32-bit version, Mecrisp, the 32-bit version, Mecrisp 64 version. On the top, you've got H1, which is done in VHDL, J1SC, which is done in spinal HDL. A lot of people must have, I mean, there are like 30 different clones, forks of the J1A on GitHub, and a lot of people have a lot more privately on their own machines. And I'm building on HANA 1 and HANA 4 off of Mecrisp processors. 25. So a lot of people are very eager for this. A lot of people are waiting for it. It's just way, way harder than I thought. Okay, and that's my talk. 20 minutes. I meant to do it 25, but I guess I got nervous. Any questions? You can also end screen share.
I posted a comment in the chat. Maybe I misunderstood what you said about you have to read in constant data from Flash. My experience, you just put it in your source code like a character ROM table I can just read in. I can compile in.
Yeah, that's yeah. So the V1 so the lattice chip is interesting because it has the single port memory, and so it's kind of inexpensive and very low power. Very low power is particularly the issue, rather opposed to dual port. But the problem is it comes in uninitialized, and you can't initialize it, and so you have to do something else. And so you basically get two choices. You can either, they have PRAM, so if you go back to the memory, so the small stuff up top is the BRAM, which you can initialize,
Oh,
and the big stuff down below is the single port, which you cannot initialize. So initially what I'm going to be doing is I'm going to be using, let's see, that's the 32 8K, maybe about a third of that for the fourth, and then copying it over to the big blocks below. But later, and then once I have all that working, then I'm going to start reading it in from the flash memory. But good question.
yeah, that's where I was confused. Yeah, I don't know the up 5K parts. I only know the 40 HX family.
Yeah, and almost all FPGAs have initializable dual port memory, or at least pseudo dual port memory. But particularly if I want to do hearing aids, then low power is really important. And so those big blocks of single port, and also, it's a lot more work to work with single port memory, but the lesson from the market is, the lesson from history is, the people with the least resources and the least expensive chip end up doing the best.
One more question. Have you looked at the GoWin FPGAs?
Yes, I have, and they're very interesting because hold on a second here. They're very interesting because they have large chunks of memory, right? And so they're generally not. The problem is they're not the open source tools. I have a Mac M1, and so these. Pardon?
So there are open source tools. So USS and XPNR support basically this 9K and 20K parts already. There is
excellent
sites that do that, and there is a new primer which is like a 25K primer also supported. It's just in the fork, but USS and XPNR will support it. No problem. So the good stuff is that yes, it has a lot of memory, and it's more than 5K lots. So it's like 20K lots. I just got a board similar to what you showed with ICE, but it's 20K part with the bootloader, the same form factor with the HDMI connector for $20 from AliExpress. So it's
awesome. So just a few things that he said there. So in synthesis, there are two things. One is you have to take the Verilog and you have to convert it to sort of a network of what the parts are actually. You have to convert to what the parts are, and that's what Yosis does. And the next thing you have to do is you have to convert that, lay that out on the actual chip, and that's what NextPRN does. And so there are multiple FPGA vendors, and NextPRN lists the FPGA boards and tools that they work with, vendors that they work with. And so this one Chinese company, GoWin, has large amounts of memory. I don't know if it's single port or dual port, but I need to take a closer look at that. And so thank you very much for that pointer. It's always good to learn from people.
Going forward, if you're here in person, say your name before you speak so that we know who the hell you are.
I have one final question.
Great.
Christopher, thanks for your presentation. It would probably be true to say that the J1 is probably a close family relative, possibly a nephew of Chuck's original Novex 4016. Certainly I've had many conversations with James Bowman, who was quite a regular at SVFIG, and certainly the J1 was inspired from the Novix device. I produced a few FPGA boards back in 2016 using the Lattice ICE 40 4K parts. And if you use Yosis and the Ice Storm tools, miraculously it becomes an 8K LUT part. Lattice were nobbling half of the LUTs in their 8K to sell a cheaper 4K. So, but yeah, it's good to see that there's a following behind what's essentially work from our predecessors. James is a silicon designer, and his J1 core is incorporated in a popular range of embedded graphic chips produced out in Taiwan.
Oh, very interesting. If there's a link, yeah.
I'll send you a link in the chat. But thanks for a great chat. Thank you.
And if any of you want to connect a Arduino to or Arduino variant to a HDMI, James Bowman has the Dazzler, which is like way totally cool.
Interesting. And so there's actually a book about Forth out of like Carnegie Mellon or something like that, about the various chips. And actually one of the James Bowman things, there's a whole chapter about the predecessors. There are like 2 predecessors that he based it on that are documented in that book. So if you want to look further, you can.
Hey, I'd like to say that I was learning Verilog at the time that this came along. Thanks, Ken. Having the Forth interpreter there is an excellent way to bring up new hardware or synthesized hardware in Verilog. For example, you do the exercises to write a simple VGA output, and then you have a Forth prompt where you can poke things in to the memory. You can design a device in synthesized Verilog that has just input and output ports and talk to those from Forth. It's really beautiful. It's beautiful to have at your command when you're bringing up a new board. So just like putting Forth on any new machine architecture. Another thing you can do is bit banging. You can write little Forth interpreted words at the console and then try it out and get precise timing. Although the J1A on the ICE stick originally it's pretty slow. There's a long latency, but it's a great tool.
Yeah, the point about debugging stuff is really important.
I think we need to move on. So
thank you very much.
Thank you, Christopher. And
I'll put the talk link in the slides in the chat.
Great. So Bill Ragsdale couldn't be here today. He may fade in at some point. So if you have questions, maybe make yourself a note. He may be here to ask them, or maybe next month or something. So Brad is working feverishly to light the fuse.